Unveiling the impossible, the black hole that breaks physics. Imagine a black hole so massive it defies everything we thought we knew about the universe. Meet GW231123, a cosmic monstrosity born from a merger that's left physicists scratching their heads, and it's about to upend decades of astrophysical theory. Over the past decade, the LIGO-Virgo-KAGRA (LVK) network has revolutionized our understanding of black holes, detecting hundreds of mergers. But none have shaken the foundations of physics like GW231123, a behemoth weighing in at **255 solar masses **, nearly double the previous record holder, 140 solar masses. This isn't just a record breaker, it's a rule breaker. The problem, black holes aren't supposed to grow this big. According to our current models of stellar evolution, stars massive enough to form such black holes should end their lives in supernovae so catastrophic that they leave no remnant behind. Yet GW231123's parents were likely two giants hovering around 100 and 140 solar masses, sizes that theoretically fall into the upper mass gap, a cosmic no man's land where black hole formation is deemed impossible. This challenges our understanding of how black holes grow, explains Dr. Mark Hannam of Cardiff University. These monsters are forbidden under standard models. But here's the twist, they're spinning dangerously fast. Both black holes were spinning at 80 to 90% of the speed limit imposed by Einstein's general relativity, making them the most rapidly spinning pair ever detected. This near-maximal spin isn't just a curiosity, it complicates the already mind-bending physics of their merger. As Dr. Charlie Hoy of the University of Portsmouth notes, modeling this system is like solving a puzzle with missing pieces. It pushes our theories to the brink. How did LIGO even detect this? Barely. LIGO's detectors are tuned for black holes around 100 solar masses, but GW231123 was so massive that its signal was barely a whisper, a 0.1 second blip at the merger's tail end. It was like hearing a faint roar from the edge of the observable universe, says one researcher. The controversy brewing. One explanation? These black holes might not have formed from stars at all but from earlier mergers of smaller black holes in dense galaxy clusters, a theory that sparks debate. Are we witnessing a new pathway for black hole growth, or is this a one-off anomaly, asks Hannam. The bigger question, what does this mean for physics? GW231123 isn't just a record, it's a warning sign that our models are incomplete. As LIGO continues to push boundaries, discoveries like this force us to confront the unknown. Will this black hole rewrite the textbooks, or are we overlooking something glaringly obvious? Your turn. Do you think this black hole proves stellar evolution models are flawed, or is there another explanation lurking? Share your theories in the comments. Largest black hole merger ever detected, two black holes collide to form a monster. Imagine two colossal black holes, each with a mass equivalent to 100 and 140 times that of our Sun, colliding in a cosmic dance. The result? A gargantuan black hole with a mass equal to 240 suns. This unprecedented event has left physicists scratching their heads, as such massive black holes were thought to be impossible according to existing astrophysical models. But here's where it gets controversial. This discovery is forcing scientists to reconsider their understanding of the universe's structure. The event, known as GW231123, was detected on November 23, 2023, by the LIGO-Virgo-KAGRA (LVK) network, a collaboration of gravitational wave detectors spread across the United States, Italy, and Japan. These detectors picked up the faint ripples in space-time caused by the monumental collision, marking the largest black hole merger ever observed through gravitational waves. This discovery challenges the standard models of stellar evolution, which suggest that black holes of this size shouldn't exist. Mark Hannam, a physicist from Cardiff University, expressed the significance of this finding, stating, "It presents a real challenge to our understanding of black hole formation." Such massive mergers defy the conventional theories of how black holes form and grow. So, what exactly are black holes? These are regions in space where gravity is so strong that nothing, not even light, can escape. Supermassive black holes, like Sagittarius A** at the center of our Milky Way, are millions of times more massive than the Sun and are known for their destructive power and mysterious nature. They remain a source of fascination and intrigue for astronomers who strive to understand these enigmatic entities. The recent merger GW231123 was observed through gravitational waves, a phenomenon first theorized by Albert Einstein in 1916. These waves are ripples in the fabric of space-time, created by some of the universe's most powerful events, such as the collision of supermassive black holes. The merger of the two black holes, each 100 and 140 times the mass of the Sun, resulted in a new black hole with a mass of 240 suns, making it the heaviest black hole merger confirmed through gravitational wave observations to date. Researchers speculate that the two black holes involved in this merger might have themselves been formed from previous mergers of smaller black holes. Amit Singh Ubhi, a research fellow at the University of Birmingham and a member of the LVK collaboration, described the discovery as a landmark achievement in gravitational wave science, highlighting its potential to open new frontiers in our understanding of black hole formation. The Laser Interferometer Gravitational Wave Observatory, LIGO, funded by the National Science Foundation, made history in 2015 with the first-ever detection of gravitational waves. Since then, LIGO has partnered with Virgo in Italy and KAGRA in Japan, leading to the discovery of over 300 black hole mergers. However, as Gregorio Carullo, a professor at Birmingham, noted, there is still much work to be done to fully analyze the recent merger and refine stellar evolution models. It will take years for the community to fully unravel this intricate signal pattern and all its implications, Carullo said. There are exciting times ahead. This discovery not only challenges existing theories but also invites us to question how many more cosmic surprises await us in the vast universe. What do you think about the implications of such massive black hole mergers? Share your thoughts and join the conversation. Breaking news: heaviest black hole merger defies astronomical theories. A groundbreaking black hole merger has shattered conventional wisdom, challenging long-held beliefs about how these cosmic giants form, and it's sparking intense debate in the astrophysics community. But here's where it gets really intriguing: the black holes involved belong to a mass range previously thought to be off-limits for stellar origin black holes, leaving scientists scrambling for new explanations. Since the landmark detection of gravitational waves in 2015, roughly 300 black hole mergers have been recorded by the International LIGO-Virgo-KAGRA (LVK) collaboration. These detectors, spread across the US, Europe, and Japan, capture the faint ripples in spacetime that occur when two black holes spiral around each other and collide. Most of the black holes noticed so far weigh in at about 10 times the mass of our Sun, sizes that align neatly with existing theories where massive stars collapse under their own gravity after running out of fuel, leaving behind black holes. However, not all stars follow this script. Very massive stars, around 200 solar masses, pose a special challenge. Theoretical models predict that such stars undergo a violent fate caused by the creation of electron-positron pairs in their hot cores, a process that saps the star's internal pressure, leading to catastrophic implosion rather than black hole formation. This phenomenon predicts a so-called mass gap where black holes weighing roughly between 60 and 130 solar masses shouldn't exist if they come from normal stellar collapse. This mass gap was put into question in 2019 when the LVK collaboration observed a merger involving black holes of 65 and 85 solar masses, nudging into the lower end of this forbidden zone. That event sent ripples through the scientific community and introduced the possibility of alternative formation methods, though ambiguity about the exact boundaries of this gap kept some hope alive that they might still stem from some variant of stellar collapse. Fast forward to now, and scientists have once again pushed the boundaries with the discovery of even heavier black holes merging, one of which clearly sits inside that forbidden mass gap. This new detection offers compelling evidence that black holes can indeed exist in the gap, states Stephen Fairhurst, spokesperson for the LIGO scientific collaboration from Cardiff University. The event, dubbed GW231123, was picked up by LIGO's twin detectors in November 2023. It stood out because the gravitational waves came at low frequencies, an indicator that the black holes were enormous. Yet the signal lasted a mere 0.2 seconds, providing only a tiny window of data, which made detailed analysis challenging. Sophie Binney from Caltech, part of the LVK team, explains, the shorter the signal, the less information we have to extract, which understandably raises uncertainties in pinpointing characteristics like mass and distance. After extensive modeling, the team concluded the merging pair involved black holes weighing approximately 103 and 137 times the Sun's mass, producing a final black hole of about 225 solar masses. Unfortunately, the brief signal meant they couldn't determine exactly where in the sky the merger happened. These findings were presented recently at the GR Maldi conference in Glasgow, drawing enthusiastic responses from experts worldwide. One such voice is astrophysicist Davide Gerosa from the University of Milano Bicocca in Italy. We've come a long way from the first unexpected discovery of 30 solar mass black holes to now witnessing behemoths exceeding 100 solar masses. This is revolutionary for our understanding of black hole populations. This naturally prompts the pressing question, how do such colossal black holes come to be? Binney suggests a hierarchical merger scenario as a plausible answer. According to this model, massive black holes grow over time through successive collisions. Imagine a family tree where each new generation results from the merging of earlier ones. But there's a hitch: mergers often deliver a recoil kick strong enough to eject the resulting black hole from dense star clusters, potentially preventing such repeated mergers. An intriguing clue lies in the spin of these black holes, how quickly they rotate on their axes. In traditional stellar origin scenarios, black holes in binary pairs are expected to have relatively small and aligned spins, reflecting their joint evolutionary path. Data from past LVK events tends to confirm this. However, when two black holes merge, the resulting single black hole usually gains a significant spin from the combined orbital motion. For GW231123, researchers assessed the spins of the two original black holes with surprising results. Despite considerable uncertainties, ranging from 20% to 50%, both seem to be spinning near their theoretical maximums, at about 80% and 90% of the maximum spin allowed. Such high spin rates strongly hint these black holes were themselves products of earlier mergers. However, Gerosa points out a puzzling detail: these spins are slightly higher than what hierarchical merger models predict, which usually hover around 70%. He speculates that further refinements in data analysis might bring these values down closer to expectations. Alternatively, the LVK team contemplates that these giant black holes could arise from massive stars merging before collapsing, a process that evades the energy instability causing the mass gap. But this theory wrestles with explaining the high spins detected in these black holes. Even amidst these mysteries, astrophysicists like Rosalba Pena of Stony Brook University believe the environment of formation could offer clues. She posits that such massive black hole mergers likely occur in regions dense with stars or enveloped in thick gas where black holes can gather extra material. Active galactic nuclei disks are one exciting candidate for such fertile grounds, she suggests. So, could there be more surprises lurking in the dark corners of our universe? Should we revise the models that have shaped black hole science for decades? And what does this mean for our broader understanding of cosmic evolution? We invite you to join the conversation. Do these findings upend your expectations, or do you see them as a natural extension of what we know? Your thoughts matter. Share your views and let's explore this cosmic enigma together.